Maybe we can move into the areas of complex analysis, which you've done major contributions there as well.
It's a subject I find very beautiful. It was my favorite subject to teach. Recently, I learned that a Midwest university, in their graduate program for people working in differential equations, don't require students to take a course in complex analysis. I was shocked.
That's blasphemy.
Absolute blasphemy, yes.
Every student, the first they encounter it, they love it. So
Yeah.
it should be taught indeed.
I got into the subject involving several complex variables. So it was a question, suppose you have in 2n real dimensions, you have n first-order differential operators with complex coefficients, just higher-order terms,
Right.
which are linearly independent. Can you make a change of variable which reduces them to the Cauchy-Riemann equations in n complex dimensions?
Right.
And there are obvious necessary conditions for that. And a student of mine, Newlander, and I proved that these conditions were sufficient. And we did it in a kind of funny way. What you have, if you write down the equations analytically, it's purely local problem.
Right.
You start with the Cauchy-Riemann operators, and you add some additional terms. And so I suggested to him, look at the case where there's just one additional term in two complex variables. That means in 4 real dimensions. And he had an idea to do that. He saw how to do that. Then together we saw how to eliminate all other terms in 2 complex variables. And we thought, okay, we've solved the problem. And it turned out it didn't work in higher dimensions. So we came up with a different kind of proof, which was you're trying to introduce new coordinates as functions of the original ones. Instead, we said, look at the original ones as functions of the new coordinates. This leads to a nonlinear system.
Right.
But the nonlinear system that has better properties and that we could treat by solving the linearized equations and just iterating.
Right.
So the trick was to make it nonlinear.
Right.
Later, Hermander found the linear proof, and Malgrange gave a proof that I like best. It's a nonlinear proof, to my mind, very original, very remarkable. Because it's known that if the original problem, if the coefficients were analytic in all variables, I mean real analytic, not complex analytic, that you could solve it using Cauchy-Kovalevsky theorem.
Right.
What Malgrange showed is that you could introduce a change of variable, but solving some nonlinear elliptic problem, which reduces the new coefficients to analytic ones. Really remarkable idea. You would never think that would work.
No.
But it's really a striking proof.
If a student suggested to me, I say, no, don't waste your time.
No, that's right. It's a nonsense. Right.
Exactly.